In this video, we're going to cover what are called tests for independence and homogeneity. So the idea of these types of tests is you have a qualitative variable, and then you have maybe different populations or a second qualitative variable, and you want to see whether or not the percentages in each category are the same for each part of the population you're talking about. For example, let's say you wanted to see whether or not being a man or a woman is independent of choosing Republican or Democrat, right? If you pick a random person and you know they're a woman, does that have a greater or a smaller chance of them being Republican as well? The example down here, also Republican Democrat, but we're talking about whether they voted yes or no to increase military spending. So the idea is we have this data, and again, this is made up data, but we're saying what they voted for, what they voted against, and we're trying to see, people always talk about Republican Party being, let's increase military spending, and the Democratic Party, let's not increase it. The question is, how do they vote? Did that really match up with what they're saying? Or is they basically voting in the same rate no matter which party they're in? So again, the idea is you're going to have these two different types of variables, or a variable and a population, however you want to think about it. You're going to be using these contingency tables that we saw a long time ago. And we're going to see how to set things up. Now, similar to the goodness of fit test, your H0 and H1 are going to be standard. There is no left tail, right tail, two tail things. Your H0 is that the two variables are in fact independent. So are independent. That means knowing one of them does not affect the likelihood of the other one. And so that means your H1 is the two variables are dependent. And that's the same for every single test for independence and homogeneity. Or you could say, if you don't want to use the word independent, you can say the two variables are homogeneous in the different situations, or they're not homogeneous. But again, it doesn't really matter exactly which word you use. The same idea, whether it's the same when broken down in the two or more categories or not the same. Once again, like we did in the goodness of fit test, we're going to have to actually calculate these expected counts and see what's going on with them. The expected counts here, before we had a formula that's just n times the relative frequency. This one's actually a little bit harder. This is going to be the row total times the column total divided by the sample size. So the idea is you look down at your table here. Let's add up on my columns. 42 plus 9 is 51. 41 plus 8 is 49. Add up on the rows. 9 plus 8 is 17. And 42 plus 41 is 83. And if you add either way, you get the total sample size of 100. So if I wanted to find out what is my expected count for, let's say, this box right here, I say, okay, my row total is 83. My column total is 51, just by looking at the row and column there. You multiply those, divide by the total sample size. Put this in our calculator here, 83 times 51 divided by 100, and I'm getting 42.33. So let's go ahead and put that in here, 42.33. And if I do the same thing here for the Democrat voted yes, I would multiply 83 times 49, and I get 40.67. For voted no for Republican would be 17 times 51 divided by 2 is 8.67. And then lastly, 17 times 49 divided by 100 is 8.33. So these are your expected counts. Once again, if you wanted to calculate the chi-squared by hand, you would take your expected counts, subtract the observed number, square it, divide by the observed number. Do that, get your chi-square thing. However, let's go ahead and show you how we're going to put this in the calculator. So let's make sure we copy down all of our data here. So we have the expected, are a little harder to remember, the 42.33, 40.67, 8.67, 8.33. And then we have the observed 42, 41, 9, and 8. So let's go over here. Now, doing hypothesis test, hit the stat button, go over to test, scroll down, and previously we had the chi-square GOF test. This type of test that we're doing now with tests for independence, that's what the one that says just chi-squared test here. And you'll notice it asks for the observed and expected like we did before. However, let me just kind of go back over here. On the chi-squared GOF test, when it asked for observed and expected, it asked for lists. However, this one that we're doing now is not asking for lists. It says this A and B thing here, these are what are called matrices. And the reason why it has to ask for that is because a list is just a single row of numbers. But you see what we're doing here is contingency tables. There's 4 slots, 2 by 2 there. So we need to go ahead and put it into the matrix format. So let me show you how to do matrix. We'll go ahead and close this out here. If you want to do a matrix input, you're going to hit second and then click to where it says matrix right here in blue. You're going to go over to where it says edit. And for A, I want a 2 by 2 matrix. So I had to pick 2 by 2. There are 2 rows and 2 columns. If I wanted, 5 rows and 3 columns, I could make that. I'm not going to give you ones that are that large though. 2 by 2 is the most common one we'll see. Maybe like a 3 by 2 or something, but 2 by 2, we'll stick to that. Now these were the observed, the actual values here, 42, 41, 9, and 8. So we get that for matrix A. Now I'm going to close out of this, go second, quit. I'm going to go back into matrix. This time I'm going to edit matrix B, make that a 2 by 2 matrix. This is going to be my expected counts, 42.33, 40.67. Notice I'm not rounding here, I'm just writing the decimal out. 8.67 and 8.33. Now I'll close out of both of those. I've input both my observed and my expected. And now I can finally get to this here, chi-squared test. Remember, my observed was in A, my expected is in B. And then you may notice they did not ask us for degrees of freedom, because it turns out that when you just put the data in this way, it can figure out the degrees of freedom for you. I will tell you the formula. It's you take the number of rows, subtract 1, take the number of columns, subtract 1, and multiply those together. Again, you don't need to do it by hand though. Hit calculate here, and you see we get P equals 0.860 or just 0.86. So let's go over here to the P value. That was 0.860 or just 86%. That means there's an 86% chance that we could just get a random sample and it would turn out to be like this. What that means is we do not reject H0. This is much bigger than the alpha. So we do not reject H0, and that means that there is not enough evidence to support the claim that Democrats and Republicans vote differently about military spending. Okay, now if we had gotten a small value, then we would say, yes, there is evidence they vote differently. Now these were just made up numbers, so you can go out and do your own research and find the actual numbers of how they voted. Feel free to do your own test here. I was trying to make the numbers work out nice though. And this is what we get. So this is how you handle tests for independence and homogeneity. And you'll kind of know it's going to be that because it's going to give you a contingency table like this. If you see that, you know it's this type of test. If you don't have that, well, then it's not going to be this type of test. And you do have to be able to do a little bit of work yourself on the expected counts here. Otherwise, you won't even be able to put it into the calculator.